The conference room at NASA headquarters fell silent as the last journalist took their seat. It was October 15th, 2025, and something was wrong. You could feel it in the air, see it in the way the officials avoided eye contact, hear it in the unusual lack of small talk. Emergency press briefings don't happen often, and when they do, they're never good news. The announcement had come just 6 hours earlier. No advance notice, no prepared media kits, no carefully crafted talking points distributed beforehand. Just a simple message. Urgent update regarding interstellar object 3I Atlas. Be there at 2 p.m. That was it. Cameras lined the back wall, their red recording lights creating a constellation of warning signals. International space agencies had representatives present. ESA, JAXA, Roscosmos. Even the typically absent Chinese National Space Administration had sent observers. Whatever was about to be revealed, it concerned everyone. The NASA administrator entered through a side door, flanked by the Director of Planetary Science and the head of the Near-Earth Object Program. Their expressions were carefully neutral, professionally composed, but their body language told a different story. These were people carrying information they wished they didn't have. The administrator approached the podium and adjusted the microphone. Behind her, a large screen remained dark, waiting. She cleared her throat and began speaking in measured tones, each word chosen with obvious care. New data had emerged from multiple observation sources. Data that required immediate disclosure to the scientific community and the public. Data that fundamentally altered our understanding of 3I Atlas. Over the past 6 weeks, she explained, an international collaboration of observatories and space-based instruments had conducted the most comprehensive analysis ever performed on an interstellar visitor. The results were definitive and deeply troubling. 3I Atlas was not behaving as any natural comet should. The mass estimates weren't just large, they were physically incompatible with observed outgassing. The chemistry wasn't just unusual, it was impossible under known formation scenarios. The trajectory wasn't just convenient, it was statistically absurd. She paused, letting those words settle like sediment in still water. Then came the statement that would dominate headlines for months. Based on accumulated evidence from 7 independent research teams across 4 continents, NASA could no longer classify 3I Atlas as a natural object with reasonable scientific confidence. The probability of all observed anomalies occurring simultaneously in a natural comet was less than 1 in 10 million. The room erupted. Questions flew like shrapnel. The administrator raised her hand for silence and nodded to her colleague. The screen behind them flickered to life, displaying a single image captured by the Hubble Space Telescope. Everyone leaned forward. What they saw would change everything. The image on the screen showed 3I Atlas as nobody had seen it before. This wasn't the fuzzy blob from amateur telescopes, or even the teardrop shape Hubble had captured in July. This was a composite image built from 6 weeks of intensive observation, using every available instrument in humanity's arsenal. And it revealed structure. The object wasn't simply shedding gas randomly as comets do. The outgassing showed organization. Jets emerged from specific points on the surface, in patterns that repeated with mechanical precision. 7 distinct emission sites, each activating and deactivating, according to a schedule that made no sense for solar heating alone. Natural comets respond to temperature. their activity follows the sun's warmth in predictable ways. 3i Atlas ignored these rules entirely. The thermal analysis made things worse. Infrared observations from the James Webb Space Telescope revealed temperature distributions that violated basic physics. Parts of the object facing away from the sun were warmer than sun-facing regions. Not by a little, by enough to eliminate measurement error as an explanation. Heat doesn't work that way naturally. Heat flows from hot to cold, from sun-facing surfaces to shadowed ones. Yet 3i Atlas seemed to generate its own warmth in specific locations, regardless of solar input. Then came the density problem. By combining the mass estimates with size measurements from multiple angles, researchers calculated the object's average density. The number came back at just under 300 kilograms per cubic meter. That's less than half the density of water ice. Natural comets range from 400 to 800. They're packed dirt and ice, compressed over billions of years. 3i Atlas was too light by almost 50%. Only two explanations existed for such low density. Either the object was mostly hollow, containing vast empty spaces inside a solid shell, or it was composed of materials unknown to natural processes. Neither option supported the comet classification. Both suggested something fundamentally different. The spectroscopic data added another impossible layer. The nickel emissions without corresponding iron weren't just unusual. They were now confirmed across multiple observation sessions. But new analysis revealed something more disturbing. The emission pattern wasn't constant. It pulsed. The nickel lines brightened and dimmed over a period of exactly 6.3 hours. Natural emission responds to temperature and solar radiation. It doesn't pulse like a heartbeat. Finally, the administrator revealed the astrometric findings. 4,022 position measurements had been analyzed using 3 independent methods. All 3 methods identified the same anomaly. At 3 specific points during observation, 3i Atlas deviated from its expected trajectory by amounts too large to be measurement error, but too small to be obvious outgassing effects. The deviations weren't random, they were corrective. Each one nudged the object back toward the ecliptic plane, maintaining its suspiciously perfect alignment with our planetary system. The evidence didn't prove artificial origin, but it eliminated every comfortable natural explanation astronomers had constructed over the previous 3 months. The mathematics of 3i Atlas had always been problematic, but the October 2025 data dump revealed just how deeply the numbers contradicted physical reality. When scientists plot mass against non-gravitational acceleration for known comets, they get a predictable relationship. Larger objects experience smaller acceleration from the same amount of outgassing. It's simple momentum conservation. 3i Atlas didn't just fall off this curve. It existed in a region of the graph where nothing natural should survive. The revised mass estimate pushed the lower limit to 42 trillion kilograms. That's 27% higher than initial calculations and represents a nucleus at least 5.8 kilometers in diameter. For perspective, that's roughly the size of a small mountain. Yet this mountain was producing gas jets vigorous enough to create a visible coma extending hundreds of thousands of kilometers into space, while experiencing acceleration so small it barely registered above instrumental noise. The rocket equation doesn't lie. When mass escapes from an object, it pushes back A person throwing a baseball on ice will slide backward. The same physics applies to comets ejecting gas. The force depends on how much gas escapes and how fast it moves. Spectroscopic measurements gave clear answers to both questions. 3I Atlas was losing approximately 190 kilograms per second, with gas velocities near 450 meters per second. Plug those numbers into the equation, and the expected acceleration should be around 300 times larger than what telescopes measured. 3 explanations existed for this discrepancy. First, the mass could be even larger than 42 trillion kilograms, pushing into realms where calling it a comet becomes meaningless. Second, the gas could be escaping much slower than spectroscopy suggested, but that contradicted direct velocity measurements from emission line widths. Third, something was actively compensating for the rocket effect, producing thrust in the opposite direction to cancel out natural acceleration. The first option required a nucleus approaching 10 kilometers in diameter, making 3I Atlas the largest interstellar object ever detected by an absurd margin. The second option required systematic errors in multiple independent measurements using different techniques. The third option required rejecting natural processes entirely. Comparison with previous interstellar visitors made the anomaly starker. Oumuamua showed acceleration of roughly 25 millimeters per day squared. 2I Borisov measured around 15 millimeters per day squared. Both values matched their observed activity levels reasonably well. 3I Atlas, despite showing far more vigorous outgassing than either predecessor, registered acceleration below 5 millimeters per day squared. The relationship was inverted. More activity produced less acceleration. Statistical analysis revealed another disturbing pattern. The residuals, the differences between predicted and observed positions, weren't randomly distributed as measurement errors should be. They showed subtle structure, small systematic deviations that accumulated over time in specific directions. The pattern suggested course maintenance rather than natural drift. Nature produces chaos. Engineering produces patterns. 3I Atlas was producing patterns. The numbers had stopped adding up to Comet months ago. Now they were starting to add up to something else entirely. Tracing 3I Atlas backward through time revealed something nobody expected. Orbital mechanics is precise, almost cruelly so. Given an object's current position, velocity, and the gravitational influences acting upon it, you can calculate where it's been with remarkable accuracy. The math works both forward and backward through time. When astronomers ran 3I Atlas through these calculations, the results defied coincidence. The object entered our solar system from the direction of the constellation Ursa Major. Nothing unusual there. Interstellar space has no preferred direction, but the precision of its approach angle told a different story. 3I Atlas arrived on a trajectory that brought it through the plane of our planetary system at almost exactly 90 degrees to the galactic disk. That's an unusual geometry, occurring naturally in perhaps one case out of 300. Running the calculations further back, accounting for the sun's motion through space and the gravitational influence of nearby stars, researchers reconstructed its path over the past million years. The object had travelled approximately 47 light-years, passing through regions of space that contained 6 stellar systems of interest. 3 of these were known to host planets. One was a system remarkably similar to our own. The closest approach to any star system occurred roughly 80,000 years ago. 3I Atlas passed within 2 light-years of a G-type star with at least 4 confirmed planets. The trajectory through that system showed the same peculiarity it demonstrated here: an approach angle that maximized observation time of the inner planets while maintaining safe distance from gravitational capture. The odds of this happening twice, by random chance, dropped below 1 in 50,000. But the truly unsettling discovery came from velocity analysis. Interstellar objects typically travel at speeds determined by their ejection from home systems and subsequent gravitational interactions. These speeds follow predictable distributions based on galactic dynamics. Most interstellar visitors arrive at velocities between 15 and 30 kilometers per second relative to the Sun. 3I Atlas entered our system at 26.4 kilometers per second, right in the middle of the expected range, perfectly unremarkable, except when you calculate the velocity needed to cross 47 light-years in the time frame indicated by stellar position reconstructions. You get 26.1 kilometers per second. The difference of 0.3 kilometers per second falls within measurement uncertainty. 3I Atlas traveled at exactly the speed required to arrive here now, having departed from the vicinity of a solar analog system 80,000 years ago. Natural objects don't maintain precise velocities over such distances and durations. They accelerate near stars, decelerate in interstellar space, and experience random perturbations from gravitational encounters. Their velocities drift. 3I Atlas showed a velocity profile consistent with powered flight and course correction capability. The path through history wasn't random drift between stars. It was a route with waypoints maintained across geological timespans. The 4.1 degree inclination had seemed curious in July 2025. By October, it had become the single most statistically improbable aspect of 3I Atlas. Understanding why requires understanding how orbits work in 3-dimensional space. Our solar system isn't just a flat disk. It has thickness, and objects can approach from any angle in a complete sphere of possible directions. That's 41,000 square degrees of sky. Interstellar objects arrive from random directions determined by the chaotic dynamics of galactic space. They could come from above the solar system, below it, or at any angle in between. The ecliptic plane, where Earth and most planets orbit, represents a thin slice through this sphere. An object approaching within 5 degrees of this plane is hitting a target that covers less than 0.1% of all possible approach angles. Initial probability calculations suggested this occurred naturally in roughly 1 out of 500 cases. Unusual, but not impossible. 3 data points strengthened the case for concern. First, refined measurements narrowed the inclination to 4.06 degrees, even closer to perfect alignment than initially measured. Second, the approach wasn't just near the ecliptic. It was timed to cross the planetary plane at a point that maximized visibility from Earth during our summer months, when Northern Hemisphere observatories dominate sky coverage. Third, the trajectory brought 3I Atlas through the plane at a speed that allowed months of detailed observation before perihelion. A team at MIT ran 10 million Monte Carlo simulations generating random interstellar approaches and checking how many satisfied all three conditions simultaneously. The answer was 147. That's a probability of 0.0015%, 1 in 68,000. Those aren't odds that inspire confidence in random chance. The alignment problem extended beyond simple geometry. When researchers examined the orbital parameters in detail, they found something more troubling. The trajectory wasn't just aligned with our planetary plane. It was aligned with our planetary plane as it existed when 3I Atlas entered the solar system, accounting for the slow wobble of Earth's axis and the gradual changes in planetary positions over time. The object had threaded a needle that moved while the needle was being threaded. Natural interstellar objects don't care about ecliptic planes. They follow gravitational physics and arrive from whatever direction their galactic journey determines. They don't arrive at convenient viewing angles during optimal observation seasons, with trajectories that maximize data collection opportunities. Yet, 3I Atlas had done exactly that. The counter-argument relied on selection bias. We can only discover objects we can observe. Perhaps dozens of interstellar visitors had passed through at steep angles, invisible to our ecliptic-focused surveys. Perhaps 3I Atlas represented the rare natural alignment that happened to be detectable. Perhaps we were seeing patterns in randomness because human brains excel at finding patterns even where none exist. But 68,000 to 1 odds make for uncomfortable coincidences. And 3I Atlas was accumulating uncomfortable coincidences at an alarming rate. The astrometric data from May through September 2025 contained over 4,000 individual position measurements. Each measurement pinpointed 3I Atlas against the background stars with precision measuring fractions of an arc-second. When you string these measurements together, you get a trajectory. When you compare that trajectory to what pure gravity predicts, you get residuals. And the residuals were telling a story nobody wanted to hear. Standard procedure in asteroid and comet tracking involves fitting observed positions to a mathematical model that includes gravitational forces from the Sun, planets, and for comets, the rocket effect from outgassing. The model produces predicted positions. Real observations deviate slightly due to measurement uncertainty and unmodeled effects. These deviations should be random, scattered equally above and below the prediction curve. 3I Atlas showed systematic deviations. At 3 distinct points during the observation period, the object's position shifted in ways that couldn't be explained by measurement error or random outgassing asymmetry. The first occurred in late June, when the residuals showed a sudden 2 arc-second deviation toward the ecliptic plane. The second happened in mid-August, again nudging toward the plane. The third occurred in early September, completing a pattern of corrections that maintained the 4.1 degree inclination with suspicious precision. Each correction was small. 2 arc-seconds translates to roughly 1,500 kilometers at 3I Atlas's distance. Tiny compared to the object's total journey. But tiny and intentional looks very different from tiny and random. The corrections occurred when the object's natural perturbations from planetary gravity threatened to increase its inclination angle. Each time the orbit started drifting away from the ecliptic plane, something pushed it back. The timing raised additional questions. All 3 corrections occurred when 3I Atlas was positioned such that Earth-based telescopes had optimal viewing geometry. Not during periods when the object was near the Sun in our sky, making observations difficult. Not when it was in southern declinations beyond northern telescope reach. The corrections happened when humanity was watching with maximum coverage and precision. Almost as if they were meant to be subtle enough to miss initially, but obvious enough to detect with careful analysis. Researchers tested alternative explanations exhaustively. Could asymmetric outgassing create this pattern? No, because the required jet orientations would produce visible coma asymmetries, not present in images. Could gravitational perturbations from asteroids create these effects? No, because no asteroids of sufficient mass were positioned correctly. Could the residuals result from systematic errors in the observational data? No, because 3 independent analysis teams using different statistical methods all identified the same deviations. The corrections were real, they were precisely timed, and they maintained an orbital configuration that defied natural probability. 3I Atlas wasn't drifting through our solar system under gravity alone. Something was flying it, making small adjustments to keep it on course. The question was no longer whether course corrections had occurred. The question was what kind of control system could execute such precise maneuvers while maintaining the appearance of a natural comet. The James Webb Space Telescope observed 3I Atlas on August 6, 2025, capturing infrared spectra with unprecedented detail. Those initial results revealed the unusual carbon dioxide to water ratio and sparked early debates about exotic formation conditions. But Webb continued observing throughout August and September, accumulating 23 additional spectroscopic sessions. The full dataset wasn't released until October 20th. What it contained changed everything. The molecular signatures went far beyond simple water and carbon dioxide. Webb detected 17 distinct chemical species in the coma, including several never before observed in any comet, natural or otherwise. Most troubling were 3 organic molecules with structures too complex to form naturally in interstellar space. These weren't simple compounds like methane or ammonia. These were long-chain hydrocarbons with specific arrangements requiring either biological processes or industrial chemistry to synthesize. One compound in particular caught the attention of astrobiologists worldwide. The spectroscopic signature matched a molecule called polycyclic aromatic hydrocarbon, with a structure containing 4 benzene rings arranged in a configuration that required specific temperature and pressure conditions to form. On Earth, this molecule appears primarily as a byproduct of incomplete combustion or industrial chemical processing. It doesn't occur naturally in space ices. The isotopic ratios added another layer of impossibility. Every element comes in different isotopes, atoms with the same number of protons but different numbers of neutrons. Natural processes create predictable isotope distributions. Solar system objects show one pattern, interstellar molecules show another. 3I Atlas showed neither. The carbon 12 to carbon 13 ratio was wrong. The nitrogen 14 to nitrogen 15 ratio was wrong. The oxygen 16 to oxygen 18 ratio was wrong. These weren't small deviations. The isotope signatures differed from both solar system and interstellar values by amounts that exceeded natural fractionation processes. Several ratios appeared artificially enriched, as if someone had separated isotopes using industrial centrifuges or nuclear processes. Natural astrophysical environments can't produce these patterns. They lack the precise control necessary to sort atoms by nuclear mass. The deuterium measurements revealed perhaps the most disturbing anomaly. Deuterium is heavy hydrogen, with 1 proton and 1 neutron instead of just 1 proton. The ratio of deuterium to normal hydrogen serves as a chemical fingerprint, telling astronomers where and when an object formed. 3I Atlas showed deuterium ratios that varied across different molecules in the coma. Water showed 1 ratio. Methane showed another. Organic compounds showed a third. This is chemically impossible in natural systems, where all molecules form from the same primordial material and should record the same deuterium signature. Only 2 processes could create this pattern. Either 3I Atlas, assembled from materials that originated in multiple different stellar environments and were somehow combined together, or the molecules were synthesized deliberately with isotope ratios chosen for specific purposes. Both explanations required abandoning natural comet origins. The Webb data wasn't showing us frozen volatiles from an alien star system. It was showing us chemistry that required laboratories. The Very Large Telescope in Chile had detected prominent nickel emission lines, without corresponding ion signatures, back in August 2025. By October, 4 additional observatories had confirmed the anomaly using independent instruments and analysis methods. What began as a curious chemical peculiarity had hardened into an undeniable physical impossibility that demanded explanation. Nickel and iron form together in stellar cores through nuclear fusion. They exist in similar abundances throughout the universe. When stars explode as supernovae, they scatter both elements equally into space. When planetary systems form from this material, nickel and iron remain chemically bonded in the same minerals and compounds. You simply cannot have large amounts of nickel without corresponding iron. It violates everything we know about cosmic chemistry. Yet 3I Atlas produced nickel emission lines with intensities suggesting substantial nickel abundance, while iron emissions remained below detection limits by factors of 100 or more. Laboratory experiments tried to recreate these conditions using every known natural process. Researchers sublimated nickel-iron meteorite samples under various temperature and pressure conditions. They bombarded mineral mixtures with ultraviolet radiation, simulating solar exposure. They tested dozens of chemical compounds that might release nickel preferentially. Every experiment failed. Natural processes released nickel and iron together, or released neither. The ratio might vary by 10 or 20%, depending on specific conditions, but nobody could suppress iron emissions by a factor of 100 while maintaining strong nickel signals. The chemistry simply didn't work that way. The emission pattern itself revealed additional structure that contradicted natural sources. Natural atomic emissions respond to temperature and solar radiation continuously. As a comet warms approaching the sun, emissions gradually increase, following smooth curves determined by physics. 3I Atlas showed step function changes. The nickel intensity would hold steady for days, then jump suddenly to a new level where it would stabilize again. Temperature doesn't change in steps. It changes smoothly. Only discrete control systems produce stepped outputs. Spectral line analysis revealed even more troubling details. The nickel emissions came from a single atomic transition, not the full spectrum of transitions expected from thermal excitation. Natural processes excite atoms to many different energy levels simultaneously, producing emission lines at many different wavelengths, with intensities following predictable patterns determined by quantum mechanics. 3I Atlas produced predominantly one transition, as if the nickel atoms were being excited by a laser tuned to a specific frequency rather than by random thermal collisions. Materials scientists offered a hypothesis that nobody wanted to hear. The nickel emissions could result from engineered surfaces designed to produce specific spectroscopic signatures. Certain metal alloys, when precisely fabricated at nanometer scales, can absorb solar energy and re-emit it at selected wavelengths. The technology is used in some satellite coatings and experimental solar cells. The emissions from 3I Atlas matched theoretical predictions for such engineered surfaces almost perfectly. Natural comets don't have engineered surfaces. They have chaotic mixtures of ice, rock, and organic compounds accumulated randomly over billions of years. The nickel-iron paradox wasn't just unusual chemistry anymore. It was looking increasingly like a designed feature intended to produce observable signals. When materials scientists examined the combined data from thermal observations, spectroscopy, and mass calculations, they encountered properties that shouldn't exist in natural objects. The challenge wasn't just explaining one unusual characteristic. It was explaining how multiple impossible properties could coexist in a single structure traveling through interstellar space. The density problem remained the foundation of the nightmare. At less than 300 kilograms per cubic meter, 3I Atlas was lighter than any known comet by almost 50%. Yet, it maintained structural integrity through gravitational stresses, temperature cycling between plus 100 and minus 200 degrees Celsius, and high-speed impacts with interstellar dust over 80,000 years of travel. Materials this light are typically fragile. Aerogels and foam structures achieve low densities but crumble under stress. 3I Atlas showed no signs of structural degradation despite its cosmic journey. The thermal properties added another impossibility. Infrared observations reveal that different regions of the object maintain different temperatures independent of solar heating. Some areas cooled and warmed with day-night cycles as expected. Other regions held constant temperatures regardless of sun exposure. This requires active thermal management, insulation systems, and internal heat sources. Natural objects have uniform thermal properties determined by their composition. They respond passively to external heating. Computer modeling attempted to find natural material combinations that could explain the observations. Researchers tested thousands of scenarios, mixing different ices, rocks, and voids in various configurations. They modeled porous structures with gas-filled cavities. They simulated layered compositions with insulating outer shells. They tried every exotic formation scenario physics allowed. None worked. To achieve the observed density required void fractions above 60%. That meant the object had to be mostly empty space. But empty space can't maintain the observed thermal properties because vacuum provides no thermal inertia to stabilize temperatures. To get the thermal behavior required solid material with high heat capacity. But solid material drove the density too high. the requirements contradicted each other fundamentally. The mechanical strength calculations revealed perhaps the most troubling impossibility. An object 5.8 kilometers across, composed of materials light enough to match the density constraints, should fragment under its own gravity if spinning at moderate rates. Natural comets typically rotate once every 6 to 18 hours. Any faster, and they risk tearing themselves apart. 3I Atlas showed brightness variations, indicating rotation periods near 6.3 hours, right at the edge of natural stability for solid objects. But the observed outgassing jets produced torques that should have altered this rotation rate over the months of observation. Natural comets spin up or slow down as asymmetric gas emission creates rotational forces. 3I Atlas maintained constant rotation despite continuous outgassing. Something was compensating for these torques, actively controlling rotation through internal mechanisms or surface features that stabilized angular momentum. Materials engineers reached an uncomfortable consensus. The combination of low density, selective thermal properties, structural integrity, and rotation control required engineered systems. Honeycomb internal structures with active thermal management, gyroscopic stabilization or momentum wheels, materials specifically designed for long-duration space travel. Natural processes don't produce these capabilities. Industrial processes do. Chapter 10. What Mars Orbiters Captured. The Mars encounter on October 3rd, 2025, offered a unique observational opportunity that wouldn't repeat. 3I Atlas passed within 30 million kilometers of the red planet, while multiple spacecraft orbited above, their instruments designed for planetary science, but capable of pointing toward distant targets. What those instruments recorded during the flyby remained classified for 2 weeks, while space agencies verified the data and consulted with international partners about appropriate disclosure protocols. The European Space Agency's Mars Express captured the first images using its high-resolution stereo camera. Despite the enormous distance, the spacecraft obtained 9 separate exposures over a 6-hour period as 3I Atlas moved against the background stars. The images showed something unexpected in the coma structure. Rather than the smooth, diffuse glow typical of gas and dust scattering sunlight, the coma displayed fine filamentary structure. Thin streamers of material extended radially from the nucleus in geometrically regular patterns, like spokes on a wheel. Natural comets occasionally show jets and streamers, but these result from active vents on the rotating nucleus and change position as rotation carries vents in and out of sunlight. The streamers in 3I Atlas remained fixed relative to the nucleus orientation across all 9 images. They didn't rotate with the object. They maintained constant positions, as if anchored to specific surface features that compensated for rotation. The Trace Gas Orbiter contributed even more troubling data. Its infrared spectrometer, designed to map trace gases in Mars's atmosphere, detected 3I Atlas against the cold background of space. The thermal emission spectrum showed 2 distinct temperature components. The expected cold component, around -100 degrees, matched predictions for a comet at that solar distance. But a second component appeared at +15 degrees Celsius, far warmer than any natural surface exposed to space should achieve without active heating. The warm component wasn't distributed uniformly. It concentrated in 7 discrete regions, matching the locations of the primary outgassing jets identified in earlier Earth-based observations. These warm spots maintained steady temperatures throughout the observation period, despite the object's rotation, carrying them alternately into sunlight and shadow. Natural surfaces heat up in sun and cool in shade, following predictable thermal curves. These regions held constant temperature independent of solar illumination. NASA's MAVEN orbiter added magnetic field data to the puzzle. Its magnetometer detected organized magnetic field structures extending tens of thousands of kilometers from 3I Atlas. Natural comets can generate weak magnetic fields through interaction between solar wind and outgassing, but these fields are turbulent and chaotic. The MAVEN data showed coherent structure with field lines aligned along specific directions. The pattern resembled magnetic fields generated by electrical currents flowing in organized loops rather than random plasma interactions. The Mars orbiter data eliminated any remaining possibility that Earth-based observations had been systematically biased or misinterpreted. Multiple independent spacecraft, using different instruments and viewing geometries, all detected the same anomalies. 3I Atlas wasn't just unusual when seen from Earth. It was unusual from every angle. The infrared data from Mars Trace Gas Orbiter had revealed warm spots maintaining constant temperatures. But detailed analysis of the thermal emissions revealed something far more disturbing than simple temperature anomalies. The spectrum of light emitted from these regions didn't match any natural material's thermal signature. It matched something designed. Every object above absolute zero emits infrared radiation. The spectrum of that emission follows a specific pattern called blackbody radiation, determined purely by temperature. Hot objects glow more at shorter wavelengths. Cool objects glow more at longer wavelengths. But all natural objects follow the same mathematical curve first described in the 1900s. This law of physics has no exceptions in nature. 3I Atlas violated it. The warm regions emitted infrared radiation with a spectrum that deviated from blackbody curves in specific, systematic ways. Certain wavelengths appeared enhanced, while others appeared suppressed. The pattern wasn't random noise or measurement error. 3 independent analysis teams confirmed the spectral distortions exceeded instrument uncertainties by factors of 10 or more. Only engineered surfaces produce non-blackbody infrared spectra. Selective emitters designed for spacecraft thermal control can radiate efficiently at some wavelengths while blocking others. Photonic crystals and metamaterials can sculpt thermal emission spectra for specific applications. These technologies exist on Earth satellites and experimental spacecraft. They don't exist on natural comets formed billions of years ago in alien star systems. The enhancement pattern revealed additional structure that deepened the mystery. The spectrum showed 3 narrow emission peaks at wavelengths of 3.5, 4.7, and 10.2 micrometers. These weren't broad thermal features spanning wide wavelength ranges. They were sharp spikes, indicating emission from specific molecular transitions or engineered resonances. The wavelengths didn't correspond to any known chemical species present in cometary ices or rocks. Thermal engineers recognized the pattern immediately. The emission peaks occurred at wavelengths where Earth's atmosphere is transparent, allowing infrared radiation to reach ground-based telescopes with minimal absorption. The 3.5 micrometer window sits between atmospheric water absorption bands. The 4.7 micrometer window falls in another atmospheric transmission region. The 10.2 micrometer window lies in the clearest part of the infrared spectrum observable from Earth's surface. The probability of 3 random emission peaks coincidentally aligning with Earth's atmospheric windows was less than 1 in 5,000. Natural objects don't care about Earth's atmosphere. Their thermal emission spectra are determined by temperature and material properties, not observational convenience for human astronomers. Yet 3I Atlas emitted enhanced infrared radiation precisely at wavelengths optimized for detection by Earth-based observatories. The infrared anomaly suggested active thermal management systems operating for a purpose beyond simple temperature control. The selective emission at specific wavelengths implied intentional signaling, or, at minimum, a designed surface with optical properties tuned for maximum detectability. Natural materials emit thermally according to physics. Engineered materials emit according to design specifications. 3I Atlas was emitting according to design specifications optimized for observation from Earth. The infrared signature wasn't a side effect of unusual composition. It was a feature engineered to be noticed by anyone with the technology to measure it. MAVEN's magnetometer data from the Mars flyby contained the most definitive evidence yet that 3I Atlas possessed internal systems incompatible with natural origins. Magnetic fields reveal what's happening inside objects in ways that optical observations cannot. The organized magnetic structure detected around 3I Atlas told a story of electrical currents, power systems, and deliberate electromagnetic engineering. Natural comets generate weak, chaotic magnetic fields through a well-understood process. As solar wind plasma encounters outgassing from the comet, it drapes around the nucleus, creating turbulent magnetic structures called induced magnetospheres. These fields are irregular, constantly fluctuating, and have strengths typically measuring between 10 and 50 nanoteslas. They show no organization beyond what solar-wind interaction naturally creates. 3I Atlas produced magnetic fields measuring over 200 nanoteslas at distances of 50,000 kilometers from the nucleus. The field strength decreased with distance following an inverse square law, indicating the source originated from the object itself rather than from solar wind interactions. But field strength alone wasn't the most remarkable feature. The topology, the three-dimensional structure of the magnetic field lines, showed organization impossible for natural plasma processes. The magnetic field formed a coherent dipole pattern like a bar magnet, aligned along the object's rotation axis. Natural magnetic fields in space are messy and tangled. They result from chaotic plasma motions and have no preferred orientation. Dipole fields require organized electrical currents flowing in specific geometric patterns. On Earth, our planetary magnetic field results from currents in the liquid iron core. On spacecraft, dipole fields come from electromagnets or current loops in electrical systems. The field orientation remained stable throughout Marvin's 6-hour observation window, despite 3I Atlas completing nearly one full rotation. Natural induced magnetospheres rotate with solar wind conditions, not with the comet nucleus. They respond to changes in the external environment. The magnetic field around 3I Atlas rotated with the object, locked to its physical structure. This requires magnetic sources embedded in or attached to the solid body, not temporary plasma interactions. Time series analysis revealed periodic fluctuations in field strength, with a period of exactly 6.3 hours, matching the optical rotation period. The fluctuations weren't random variations. They followed a sinusoidal pattern, indicating systematic changes tied to rotation. Something inside 3I Atlas was generating time-varying magnetic fields synchronized with its spin. The power requirements for generating magnetic fields this strong over such large volumes staggered electrical engineers. Maintaining 200 nanotesla fields at 50,000 kilometer distances requires electrical currents flowing through conductors, or plasma, with powers measuring in the kilowatt to megawatt range. Natural comets have no power sources beyond solar heating and gravitational energy. They cannot sustain electrical currents over geological timescales. 3I Atlas was generating organized magnetic fields requiring active power systems, electromagnetic coils or equivalent current sources, and control systems maintaining field orientation relative to the rotating structure. These are characteristics of spacecraft electrical systems, satellite power generation, and engineered electromagnetic devices. They are not characteristics of frozen rock and ice drifting through space. SETI began monitoring 3I Atlas on July 15, 2025, just 2 weeks after discovery. The comprehensive radio survey employed 32 antennas across 6 continents, scanning frequencies from 1 MHz to 100 GHz. This represented the most thorough electromagnetic spectrum analysis ever conducted on an interstellar object. The campaign ran continuously for 94 days, accumulating over 2,000 hours of observation time. They detected nothing. The silence wasn't surprising initially. Nobody expected interstellar objects to broadcast radio signals. Natural cosmic sources emit radio waves through various mechanisms, but discrete objects like comets and asteroids typically remain radio quiet, except for occasional plasma interactions. Yet, as evidence mounted that 3I Atlas might not be natural, the absence of radio emissions became increasingly significant. Advanced technological civilizations use electromagnetic radiation for communication and sensing. Radio frequencies offer advantages for long-distance transmission, penetrating dust and plasma that blocks visible light. Any spacecraft operating in interstellar space would likely employ radio systems for communication with its origin point or for sensing its environment. The complete absence of such signals suggested either advanced signal discipline or communication methods beyond radio frequencies. The monitoring campaign specifically searched for narrowband emissions characteristic of artificial transmitters. Natural cosmic radio sources produce broadband noise across wide frequency ranges. Technological sources concentrate power into narrow channels for efficient information transmission. SETI's algorithms could detect narrowband signals billions of times weaker than broadband background noise. They found nothing above noise levels across the entire surveyed spectrum. Analysis extended beyond simple signal detection to searching for patterns in the noise itself. Random noise has statistical properties that follow predictable distributions. Information-bearing signals, even if encrypted or compressed, show subtle deviations from pure randomness. researchers applied every known technique for extracting weak signals from noise. They looked for periodic modulations, frequency drifts, polarization patterns, and correlation structures. All results came back consistent with pure instrumental noise. The negative results told a story through absence. If 3i Atlas possessed radio systems, they were either powered down, operating at frequencies outside the surveyed range, or employed such sophisticated signal processing that emissions appeared indistinguishable from natural noise. All three possibilities required deliberate engineering. Natural objects don't have radio systems to power down. They don't choose transmission frequencies. They don't encrypt signals. Researchers considered exotic communication methods that might explain the silence. Optical laser communications would be invisible to radio searches. Neutrino beams could transmit information without electromagnetic signatures. Quantum entanglement-based systems might enable communication without classical signal propagation. Each possibility pushed further into speculative technology beyond current human capability. The most unsettling interpretation suggested intentional stealth. An object designed for reconnaissance might minimize electromagnetic emissions to avoid detection. Military satellites employ similar strategies, maintaining radio silence except for brief, highly directional transmissions. 3i Atlas might be deliberately quiet, observing rather than broadcasting, collecting data while revealing minimal information about its nature or purpose. The radio silence combined with visible anomalies created a troubling profile. Active systems maintaining trajectory, thermal management, and magnetic fields, but complete electromagnetic quietness across all monitored frequencies. This combination suggested sophistication and intent. Brightness measurements of 3i Atlas accumulated over 5 months revealed periodic variations that went far beyond simple rotation. Every object in space changes brightness as it spins, presenting different surface areas and reflectivity to observers. These variations typically follow smooth, predictable curves determined by shape and spin rate. 3i Atlas showed brightness changes that followed mathematical patterns no natural rotation could produce. The primary variation occurred with a period of 6.3 hours, consistent with rotational spin. But superimposed on this main cycle were secondary variations at precise fractional periods. A strong signal appeared at 3.15 hours, exactly half the rotation period. Another appeared at 2.1 hours, precisely 1/3. Additional peaks showed up at 1.575 hours and 1.26 hours, corresponding to 1/4 and 1/5 of the main period. These harmonic relationships are signatures of geometric regularity. Natural objects have irregular shapes with random bumps and craters that produce complex non-periodic brightness variations. Engineered objects with symmetrical structures produce harmonics because identical features repeat at regular intervals around the rotation axis. A spacecraft with 4 equally spaced solar panels would show brightness peaks at quarter rotation intervals. An object with 6-fold symmetry would produce peaks every 60 degrees. The amplitude of these variations provided additional clues about surface properties. The brightness changed by 37% between maximum and minimum, far larger than typical asteroids or cometary nuclei, which vary by 5 to 15%. Large amplitude variations require either extreme elongation, like a tumbling cigar, or highly contrasting surface materials, with some areas much more reflective than others. The stable rotation period ruled out tumbling. The harmonics ruled out random surface variations. The brightness pattern indicated discrete, regularly spaced features with different reflective properties. Color measurements added another layer of structure. Brightness variations didn't occur uniformly across all wavelengths. Blue light showed larger amplitude changes than red light. The blue to red ratio varied systematically throughout the rotation cycle, reaching maximum values at specific rotation phases that coincided with the harmonic brightness peaks. Natural materials don't produce wavelength-dependent brightness variations with this kind of organization. Selective coatings and engineered surfaces do. Polarization analysis revealed the most definitive evidence of surface organization. Light reflected from natural rocky or icy surfaces becomes partially polarized, with the degree of polarization depending on viewing angle and surface roughness. 3-eye atlas showed polarization signatures that varied systematically with rotation phase and exhibited sharp transitions at specific angles. The polarization degree jumped from 15% to 35% within narrow rotation phase ranges, then dropped back sharply. Natural surfaces produce smooth polarization curves without abrupt transitions. The optical variability pattern painted a picture of an object with geometric regularity in its structure and systematic variation in surface properties distributed in organized patterns. The harmonics indicated symmetry. The color variations indicated compositional control. The polarization transitions indicated discrete surface features with engineered optical properties. Natural objects rotating in space don't produce this combination of characteristics. Manufactured objects with designed surface features do. 3-eye atlas was reflecting light like something built rather than something formed. 3-eye atlas reached perihelion, its closest approach to the Sun, on the afternoon of September 28, 2025. The timing placed the object on the far side of the Sun from Earth's perspective, creating an observational blackout that lasted from mid-September through early November. This geometric configuration meant that during the most thermally active phase of its passage, when solar heating peaked and comet activity should maximize, 3-eye atlas remained largely invisible to Earth-based telescopes. Only spacecraft positioned elsewhere in the solar system could observe what happened during those critical weeks. Parker Solar Probe occupied a unique vantage point. The NASA spacecraft orbits close to the Sun, studying solar wind and coronal dynamics from distances where few instruments can survive. On September 29th, Parker's Wide-Field Imager for Solar Probe, known as WISPER, captured 3-eye atlas at a distance of just 42 million kilometers. The images showed behavior that contradicted every prediction based on natural comet physics. Comets typically brighten dramatically as they approach the Sun. Increased solar heating vaporizes more ice, producing larger comas and more prominent tails. Activity peaks near perihelion, then gradually declines as the comet recedes. 3-eye atlas did the opposite. As it approached perihelion through September, brightness declined steadily. The coma contracted rather than expanded. Outgassing rates measured from spectroscopic line intensities dropped by 40% between mid-September and perihelion passage. This inverted behavior made no thermal sense. Solar flux at perihelion was 3.8 times higher than at discovery in early July, when the object showed vigorous activity. Temperature should scale with solar flux, and activity should scale with temperature. Yet 3I Atlas became less active precisely when physics demanded maximum activity. Natural volatiles don't stop sublimating when heated more intensely. The whisper images revealed additional anomalies in coma structure during perihelion passage. The familiar jets and streamers visible in earlier observations had vanished. The coma appeared smooth and nearly featureless, lacking the complex structure expected from multiple active vents responding to peak solar heating. It was as if someone had turned off the outgassing, just as natural processes should have turned it up. Temperature measurements from Parker's thermal sensors detected another impossibility. Surface brightness temperatures on the sunward side reached only 75 degrees Celsius, far below the 130 degrees predicted for a dark comet surface at that solar distance. Something was preventing the surface from heating normally, either through highly reflective coatings that rejected sunlight, or through active cooling systems that removed absorbed heat. The timing correlation between Earth's observation geometry and activity levels raised uncomfortable questions. 3I Atlas displayed maximum activity when Earth-based telescopes had optimal viewing access. Activity declined precisely when the object moved behind the Sun, becoming unobservable from Earth. The correlation was near perfect across the entire observation period from July through September. Natural comets respond to solar heating, not to whether Earth can see them. The perihelion behavior suggested awareness of observation geometry and deliberate modulation of visible activity to maximize detectability during favorable viewing periods, while minimizing exposure during the critical perihelion phase. The International Astronomical Union convened an emergency session on October 22, 2025, the first unscheduled meeting in the organization's 107-year history. The agenda contained a single item, determining the appropriate classification for 3I Atlas. What should have been a straightforward taxonomic discussion became a fundamental debate about how science handles objects that defy existing categories. The IAU's classification system divides solar system objects into well-defined groups based on observable characteristics. Asteroids are rocky bodies without atmospheres. Comets are icy bodies that develop comas and tails when heated. Planets are massive enough to clear their orbits. The system works because natural objects fit cleanly into these categories based on composition, behavior, and formation history. 3I Atlas fit none of these definitions comfortably. It showed comet-like activity with a visible coma and outgassing, satisfying the basic comet criteria. But the activity patterns, chemical composition, and physical properties diverged so drastically from known comets that retaining the classification seemed scientifically dishonest. The object acted like a comet, only superficially, while violating fundamental comet physics in nearly every measurable parameter. The debate centered on whether astronomy needed a new classification category for objects of potentially artificial origin. Some argued that creating such a category would legitimize speculation without definitive proof. Others countered that refusing to acknowledge the possibility when evidence pointed strongly in that direction represented scientific cowardice disguised as rigor. A proposal emerged for an intermediate designation, anomalous interstellar object, or AIO. This classification would acknowledge that certain visitors display characteristics incompatible with natural formation and evolution, while avoiding explicit claims about artificial manufacture. Objects classified as AIO would require extraordinary evidence and pass strict criteria, including multiple independent anomalies, statistical improbability of natural occurrence, and failure of all conventional explanations. 3I Atlas met every proposed criterion. Density incompatible with known materials. Isotope ratios impossible for natural fractionation. Magnetic fields requiring power sources. Thermal properties indicating active management. Trajectory corrections maintaining improbable orbital alignment. Optical signatures suggesting geometric regularity. Each anomaly alone might permit creative natural explanations. Their simultaneous occurrence in one object exceeded reasonable bounds for coincidence. The counter-argument emphasized that humanity had observed only 3 interstellar visitors total. Sample sizes this small couldn't support confident claims about what constitutes normal versus anomalous behavior for such objects. Perhaps interstellar space produces objects with properties we don't understand through natural processes we haven't discovered. Perhaps our models are incomplete rather than the objects being artificial. This philosophical tension reflected deeper anxieties about the implications of classification. Calling 3I Atlas a comet implied we understood it within existing frameworks. Creating a new category implied we faced something unprecedented and potentially revolutionary. The IAU postponed the decision, requesting additional data and analysis. But the debate revealed that the scientific community had already passed a threshold. 3I Atlas had forced astronomers to seriously consider that not everything in space is natural. The question wasn't whether comets could be something else. The question was whether we were ready to admit that something else might be visiting us. The discovery of 3I Atlas prompted astronomers to re-examine data from Oumuamua, our first confirmed interstellar visitor from 2017. The original analysis had revealed puzzling characteristics that sparked years of debate: extreme elongation or pancake shape, mysterious acceleration without visible outgassing, tumbling rotation, and reddish surface coloration, unlike typical comets. At the time, these anomalies seemed like isolated curiosities. In light of 3I Atlas, they began forming a pattern. Researchers reprocessed Oumuamua's astrometric data, using the same advanced techniques applied to 3I Atlas. The original analysis had detected non-gravitational acceleration of approximately 25 millimeters per day squared, but found no corresponding outgassing to explain it. The new analysis revealed something previously missed. The acceleration wasn't constant. It varied systematically with Oumuamua's rotation, reaching maximum when specific surface features faced the Sun, and minimum when those features rotated away. This rotation-dependent acceleration pattern matched theoretical predictions for a tumbling solar sail, or an object with discrete active surfaces, rather than uniform outgassing from an irregular icy body. Natural comet outgassing produces acceleration that varies with solar distance and temperature, but shows no correlation with rotation phase. Oumuamua's acceleration, locked to its tumbling motion, suggested forces generated by oriented surface features. The probability analysis revealed the most troubling connection. Interstellar object encounter rates, based on stellar dynamics and planetary formation models, predict one detection every few decades with current survey capabilities. Yet humanity detected 2 interstellar visitors within 8 years. The probability of this occurring by chance, if the true encounter rate matched theoretical predictions, was less than 4%. Either the models were wrong by large factors, or we were witnessing a statistical cluster. More disturbing was the correlation in anomalies. Both objects showed properties incompatible with natural comet physics. Both displayed behaviors suggesting artificial characteristics. Both arrived on trajectories that maximized observation opportunities. Oumuamua passed close to Earth in October 2017, when Northern Hemisphere telescopes had optimal viewing angles. 3I Atlas arrived aligned with the ecliptic during summer observation season. The probability of 2 random visitors, both arriving with favorable observation geometry, dropped below 1%. The chemical data added another parallel. Oumuamua showed unusual spectroscopic features in the limited data obtained before it faded from view. Its surface reflectance spectrum lacked the deep ice absorption features expected for cometary materials. 3I Atlas displayed isotopic anomalies and organic molecules inconsistent with natural formation. Both objects carried chemical signatures that didn't match known populations of solar system bodies or interstellar ice. Critics argued that focusing on similarities between 2 objects from a sample of 3 represented classic confirmation bias. With so few data points, finding correlations was meaningless statistically. Perhaps the third interstellar visitor, 2I Borisov from 2019, represented normal behavior, while the other 2 were separate rare anomalies. But 2I Borisov was the outlier. It behaved exactly like a conventional solar system comet in every measurable property. The anomalous visitors outnumbered the normal 1 2 to 1. That ratio suggested something systematic rather than random variation. Oumuamua and 3I Atlas weren't isolated mysteries. They were connected data points in a pattern humanity was only beginning to recognize. Population synthesis models predict how many interstellar objects of various sizes should pass through our solar system based on stellar formation rates, planetary system architectures, and ejection mechanisms operating throughout galactic history. These models incorporate decades of research on planet formation, stellar dynamics, and observed debris populations. They all make the same fundamental prediction: small objects vastly outnumber large ones. The size distribution follows what's called a power law. For every object 10 kilometers across, there should be roughly 1,000 objects 1 kilometer across, and 1 million objects 100 meters across. This scaling relationship emerges naturally from collision physics and gravitational ejection processes that fragment larger bodies preferentially and eject smaller pieces more efficiently. Every asteroid belt and debris disk in the universe follows similar scaling laws. Current survey capabilities can detect interstellar objects down to approximately 100 meters diameter if they pass within a few astronomical units of Earth and develop visible comas. Objects between 100 meters and 1 kilometer should dominate discovery statistics. We should find dozens of small visitors before encountering our first giant. Yet, in 8 years of systematic searching, humanity detected 3 interstellar objects: one possibly elongated object several hundred meters long, one roughly 1 kilometer comet, and one potential 5 to 6 kilometer giant. The sequence is backwards. It's like fishing in a lake and catching a trophy bass on your first cast, a medium perch on your second, and a record-breaking pike on your third, while never catching the abundant minnows that should dominate any healthy ecosystem. Either the lake contains only trophy fish, which violates ecological principles, or something is seriously wrong with how we're fishing. Updated models incorporating the latest exoplanet statistics and improved ejection efficiency calculations made the problem worse. Refined predictions suggested encounter rates 10 times higher than earlier estimates, with size distributions even more strongly weighted towards small objects. The models predicted we should have detected between 50 and 200 small interstellar visitors by 2025. We had detected 3 objects, 2 of which were anomalously large. Observational bias could explain some discrepancy. Perhaps small objects pass through without developing visible comas that trigger detection algorithms. Perhaps our surveys miss objects with high inclinations or unusual orbits. But bias can't explain why the detected objects cluster toward large sizes. Bias should work in the opposite direction, making small objects easier to find relative to their true abundance. The alternative explanation suggested that natural interstellar debris follows predicted distributions. But we're not detecting natural debris. We're detecting something else that doesn't follow natural size scaling. Manufactured objects don't obey power law size distributions. They come in whatever sizes their builders design. A survey detecting primarily artificial visitors might find large objects preferentially if large sizes serve specific mission purposes better than small ones. The population statistics breakdown meant one of 3 possibilities held true. Either our understanding of interstellar object populations was fundamentally wrong, or our detection methods were bizarrely biased in unexpected ways, or we weren't detecting a natural population at all. Each option had profound implications. The third option had the most profound implications of all. Aerospace engineers and spacecraft designers were asked to reverse engineer 3I Atlas based purely on observed properties. The exercise assumed artificial origin and asked what design requirements and engineering solutions would produce the measured characteristics. The results revealed a coherent architecture that addressed specific mission needs using technologies beyond current human capability, but consistent with physical laws. The low density of less than 300 kilograms per cubic meter suggested a hollow structure with thin outer shells and minimal internal mass. Engineers proposed a design similar to inflatable space habitats or gossamer spacecraft that achieve large volumes with minimal material. A honeycomb framework covered by multi-layer insulation could provide structural integrity while maintaining the observed density. This architecture would also explain the thermal anomalies, as insulation layers could regulate heat flow independent of solar exposure. The stable rotation and resistance to outgassing torques pointed toward active attitude control. Reaction wheels or control moment gyroscopes mounted internally could counteract unwanted rotation changes. These systems are standard on satellites, but require power sources and control computers to operate continuously. The 6.3-hour rotation period might be deliberately maintained rather than naturally stable, chosen to simulate realistic comet behavior while simplifying thermal management by ensuring all surfaces receive periodic solar exposure. The organized magnetic field required electrical current loops or permanent magnets embedded in the structure. For a field strength of 200 nanoteslas at 50,000 kilometers, engineers calculated minimum current requirements around 100,000 amperes, flowing through loops several kilometers in diameter. This power level suggested either nuclear generators or advanced solar power systems with energy storage. Batteries couldn't sustain such currents over the 80,000-year journey time. Nuclear decay or matter-antimatter reactions remained viable options. The course correction capability implied propulsion systems with extremely high efficiency. The observed trajectory adjustments totaled less than 50 meters per second velocity change, tiny by rocket standards. But executing these adjustments precisely while maintaining the appearance of natural motion required sophisticated guidance and thrust vectoring. Ion drives or photon pressure systems could provide the needed precision with minimal propellant consumption. The selective thermal emission and engineered spectroscopic signatures suggested surface coatings designed for specific optical properties. Metamaterials and photonic crystals could produce the observed non-blackbody spectra while maintaining structural integrity. These coatings might serve dual purposes, regulating internal temperature and generating detectable signals at wavelengths. Optimized for Earth-based observation, the outgassing presented the greatest engineering challenge. Creating a visible coma while minimizing actual mass loss and avoiding significant rocket effects required careful rate control and possibly recycling systems. Engineers proposed storing volatiles in internal reservoirs and releasing them through vents at controlled rates. The gas could be cold gas from cryogenic storage rather than sublimated ice, explaining why outgassing didn't follow natural temperature responses. The complete design painted a picture of a reconnaissance platform optimized for long-duration interstellar travel and passive observation, large volume for instruments and systems, low density for minimizing propulsion requirements, active thermal control for protecting sensitive equipment, magnetic fields for radiation shielding or plasma interactions, precise attitude control for pointing sensors, engineered visibility for detection by target civilizations. Every observed anomaly served identifiable engineering purposes. The design made sense as a spacecraft, even if it made no sense as a comet, crossing 47 light-years of interstellar space in 80,000 years, requires maintaining an average velocity near 26 kilometers per second for the entire journey. This speed represents 1/10,000th the speed of light, far below relativistic velocities, but extraordinarily fast by conventional rocket standards. Achieving and maintaining such velocities over geological timescales presents engineering challenges that illuminate what 3I Atlas must be if it truly traveled this route deliberately. Launch from the origin system required accelerating 42 trillion kilograms to escape velocity and then to interstellar cruise speed. Chemical rockets can't accomplish this. The rocket equation, which governs all reaction-based propulsion, becomes impossibly demanding for such large masses. Even nuclear thermal rockets struggle with the mass ratios needed. The most plausible solutions involve either extremely long acceleration times, using low-thrust, high-efficiency propulsion, or external energy sources that don't require carrying propellant. Solar sails could provide acceleration near the origin star using photon pressure. A sail several kilometers across with reflectivity above 99% could accelerate the observed mass to interstellar speeds over decades of spiral outward from the parent star. This method requires no onboard propellant and matches the large size and low density observed in 3I Atlas. The hollow structure and geometric regularity suggested by optical observations fit solar sail architecture naturally. Alternatively, laser-pushed light sails could achieve higher velocities with shorter acceleration times. If the origin civilization possessed megawatt or gigawatt laser arrays, they could propel spacecraft to interstellar speeds within years rather than decades. This requires advanced technology, but no physics beyond current understanding. Several proposed human interstellar missions employ similar concepts for reaching nearby stars within centuries. The journey duration of 80,000 years raised questions about system longevity and purpose. Electronic systems degrade over time from cosmic ray damage and material aging. Maintaining functionality across such timescales requires either extremely robust construction with massive redundancy or self-repair capabilities using nanotechnology or equivalent systems. Both approaches push engineering far beyond current human technology, but don't violate physical laws. The cosmic ray environment in interstellar space delivers radiation doses that would destroy unshielded electronics within millennia. 3I Atlas needed either heavy radiation shielding, which conflicts with low density requirements, or radiation-hardened systems that tolerate damage without failure. The observed magnetic field could serve as active radiation shielding, deflecting charged particles around sensitive components, much as Earth's magnetic field protects our surface. Trajectory maintenance over 80,000 years required navigation systems that could measure position and velocity relative to distant stars, compute course corrections, and execute propulsive adjustments with precision better than 1 kilometer per second. Star trackers and inertial reference systems could provide necessary accuracy. Small propulsive adjustments every few decades or centuries would prevent accumulated drift from stellar perturbations. The mission profile suggested reconnaissance or exploration rather than colonization. The velocity was too high for easy capture into orbit around the target star. 3I Atlas would perform a flyby, gathering data during a brief passage through the inner solar system before continuing into interstellar space. This architecture maximizes the number of systems that can be surveyed with minimal energy expenditure per target. A single vehicle could visit dozens of stellar systems over millions of years if properly designed for longevity and self-maintenance. The power requirements for 3I Atlas's observed capabilities dwarfed anything achievable with conventional energy sources. Generating magnetic fields, maintaining active thermal control, executing trajectory corrections, and operating for 80,000 years required energy systems that could function reliably across geological timescales, while providing steady power in the kilowatt to megawatt range. Solar power offered one possibility. At Earth's distance from the Sun, solar panels receive about 1,300 watts per square meter. An object 5.8 kilometers in diameter has a cross-sectional area of 26 square kilometers. If 10% of this area consisted of solar panels with 20% efficiency, the system could generate roughly 7 megawatts of power when pointed towards the sun. This exceeds the estimated requirements for magnetic field generation and other active systems by comfortable margins. But solar power has limitations for interstellar travel. Beyond a few astronomical units from any star, solar flux drops to negligible levels. During the 80,000-year journey between stellar systems, 3I Atlas would have spent most of its time in deep space, where solar panels generate essentially zero power, unless the vehicle entered hibernation during transit and activated only when entering target systems. Solar power alone couldn't sustain continuous operation. Nuclear power provided a more plausible solution for long-duration missions. Radioisotope thermoelectric generators convert heat from radioactive decay into electricity using thermocouples. RTGs power deep space probes like Voyager and New Horizons that operate far from the sun. The technology is mature and reliable. However, conventional RTGs using plutonium-238 have half-lives around 88 years. After 80,000 years, over 99.9% of the original fuel would have decayed, leaving insufficient heat for power generation. Longer-lived isotopes offer better prospects. Plutonium-244 has a half-life of 80 million years. Curium-250 extends to 9,000 years. Using such isotopes would maintain power output across interstellar transit times. The mass penalty for carrying sufficient nuclear fuel could be acceptable, given the low overall density observed in 3I Atlas. A few thousand kilograms of radioisotopes distributed throughout the structure could provide kilowatt-level power indefinitely. More exotic possibilities included fusion reactors using hydrogen or helium isotopes. Fusion offers energy densities millions of times higher than chemical reactions and doesn't produce long-lived radioactive waste. A compact fusion reactor massing a few tons could power the vehicle throughout its mission if the technology could be made reliable enough for autonomous operation over geological timescales. Human fusion research hasn't achieved this reliability yet, but the physics permits it in principle. The most speculative option involved matter-antimatter reactions. Annihilating just 1 kilogram of antimatter with 1 kilogram of matter releases energy equivalent to 43 megatons of TNT. A few kilograms of stored antimatter could power a mission lasting millions of years. The engineering challenges of storing antimatter safely for such durations are formidable, but not physically impossible. Magnetic traps and sophisticated vacuum systems could theoretically contain antimatter indefinitely. The power source problem had no clear answer, but it had plausible solutions. Nuclear systems using long-lived isotopes represented the most conservative approach. Fusion or antimatter systems offered higher performance at the cost of greater technological sophistication. All options required technology beyond current human capability, but within known physics. 3I Atlas either carried energy systems we don't yet understand, or proved that advanced engineering could solve problems we consider barely feasible. NASA faced an unprecedented decision in late October 2025. The Juno spacecraft, currently orbiting Jupiter and conducting detailed studies of the gas giant's atmosphere and magnetic field, could potentially be redirected toward an intercept with 3I Atlas during its March 16th, 2026 approach to Jupiter. The trajectory calculations were feasible. The fuel reserves were barely sufficient, but executing the maneuver would end Juno's primary mission permanently. The engineering analysis showed that Juno could reach an intercept distance of approximately 800,000 kilometers from 3I Atlas, using a series of Oberth effect maneuvers near Jupiter. At closest approach, the spacecraft's instruments could collect data impossible to obtain from Earth-based telescopes. Magnetometer readings would definitively characterize the organized magnetic field. Infrared sensors would map thermal emissions with kilometer-scale resolution. Camera systems could potentially resolve surface features and structures. The scientific value was enormous, but not infinite. Juno carried instruments designed for planetary science, not close encounters with small bodies. The magnetometer and particle detectors would provide excellent data. The infrared spectrometer and microwave radiometer could contribute valuable measurements, but the camera system lacked the resolution for detailed surface imaging at 800,000 kilometer distances. What Juno could learn about 3I Atlas would be significant but incomplete. The cost was definitive. Redirecting to intercept would expend all remaining fuel reserves. Juno could not return to Jupiter orbit afterward. The extended mission studying Jupiter's polar regions, deep atmospheric dynamics, and radiation environment would end immediately. Years of planned observations would be sacrificed for a single brief encounter with an interstellar visitor. Congressional pressure mounted throughout October. Representatives argued that studying potentially artificial objects took priority over incremental improvements to Jupiter science. Public interest in 3I Atlas far exceeded public interest in Jupiter's atmospheric jets. The opportunity was unique and fleeting. Missing it meant waiting decades or centuries for another chance at close-range interstellar object observations. Space agency leadership hesitated. The decision set precedent for how humanity prioritizes scientific objectives when faced with unprecedented discoveries. Abandoning established missions for speculative targets could undermine long-term planning and mission architecture. But ignoring potentially revolutionary opportunities to preserve routine observations seemed equally short-sighted. International partners complicated matters further. ESA and JAXA had contributed instruments to Juno and expected full mission duration. Unilateral American decisions to redirect the spacecraft without consensus could damage future collaboration. Yet building international consensus required time the closing intercept window didn't permit. By October 25th, the decision could wait no longer. The trajectory calculations required execution within 10 days to achieve optimal intercept geometry. NASA scheduled an emergency meeting for October 27th to make the final call. The Juno dilemma crystallized the larger question facing humanity. How aggressively should we pursue evidence that we're not alone? The orbital mechanics defining the Jupiter encounter allowed only one viable intercept opportunity. 3I Atlas would pass Jupiter on March 16th, 2026, at a distance of 53.6 million kilometers. Juno orbits Jupiter with a highly elliptical trajectory, swinging close to the planet every 53 days, before arcing outward again. Aligning Juno's position with 3I Atlas's trajectory, while the spacecraft possessed sufficient velocity to reach intercept distance, required executing maneuvers during a specific window. The optimal trajectory solution involved 3 propulsive burns. The first burn would occur on November 7th, 2025, during Juno's close approach to Jupiter. This Oberth effect maneuver would raise the orbit's aphelion, the furthest point from Jupiter, sending the spacecraft on a trajectory that intersected 3I Atlas's path. The second burn in mid-January would fine-tune the trajectory based on updated position measurements. The third burn in early March would provide final corrections for closest approach. Each burn carried risk. Juno's propulsion system was designed for orbital adjustments around Jupiter, not major trajectory changes for interstellar intercepts. The total velocity change required approached the limits of available fuel reserves. Engineers calculated success probability at 78%, accounting for instrument uncertainties, fuel gauge accuracy, and thruster performance variations. 22% probability of mission failure meant losing both the Jupiter science and the intercept attempt. The intercept distance of 800,000 kilometers represented a compromise between scientific return and mission risk. Closer approaches would provide better data, but required more fuel and higher precision. The chosen distance allowed Juno's instruments to collect meaningful measurements while preserving margins for navigation uncertainties and unexpected trajectory adjustments. The observation window during intercept would last approximately 8 hours as 3I Atlas passed through Juno's field of view. The magnetometer could collect continuous data throughout this period, building detailed maps of magnetic field structure. The infrared instruments would capture thermal emission spectra across multiple wavelengths. The camera system would obtain dozens of images showing 3I Atlas from different angles as the relative geometry changed. After intercept, Juno would continue outward from Jupiter on a hyperbolic escape trajectory. The spacecraft would leave the Jovian system permanently, becoming a heliocentric satellite orbiting the Sun in the asteroid belt region. Communication would remain possible for years as onboard systems continued functioning, but no further Jupiter science would occur. The closing window created urgency that overrode normal decision-making processes. Space missions typically involve years of planning and review. The Juno redirect decision had to be made within days, based on incomplete analysis and uncertain outcomes. By October 30th, 2025, NASA had to commit or abandon the opportunity forever. The intercept window was closing and wouldn't open again in any of our lifetimes. The global reaction to NASA's October 15th announcement revealed how deeply 3I Atlas had penetrated international consciousness. Within hours of the press conference, space agencies across 6 continents issued statements acknowledging the findings and committing resources to continued observation. The coordinated response suggested prior communication between agencies, quiet discussions, preparing for public disclosure of what many suspected privately for weeks. The European Space Agency released its own analysis on October 17th, confirming NASA's conclusions based on independent examination of Mars orbiter data and ground-based telescope observations. ESA's statement went further than NASA's careful wording, explicitly stating that natural explanations for the observed phenomena had been exhausted and that artificial origin hypotheses deserved serious scientific consideration. The language represented a significant departure from institutional conservatism that typically characterizes space agency communications. China's space program surprised observers by releasing previously classified observations from its Chang'e Lunar Farside Relay satellite. The spacecraft had detected 3I Atlas in August, using radio instruments designed for lunar communication support. The data showed anomalous radar reflections, with characteristics inconsistent with natural icy or rocky surfaces. The reflectivity pattern suggested metallic structures, or at minimum materials with electromagnetic properties, unlike any known cometary composition. China's decision to declassify and share this data indicated willingness to prioritize scientific cooperation over strategic secrecy. Russia's space agency contributed tracking data from military satellite surveillance networks typically kept confidential. The precision astrometry from these systems exceeded civilian telescope capabilities and helped constrain the trajectory corrections identified in NASA's analysis. Roscosmos also confirmed independent detection of organized magnetic field structures using magnetometers aboard interplanetary missions not publicly disclosed previously. The transparency marked a notable shift from historical Russian preference for information control. Japan's space agency announced immediate reprogramming of the Hayabusa 2 extended mission spacecraft to attempt distant observations during 3I Atlas's outbound journey. Although the spacecraft couldn't achieve close approach, its instruments designed for asteroid characterization could contribute additional data points from a different vantage point in the solar system. The commitment of mission resources demonstrated how high priority the international community placed on gathering maximum information. India's Space Research Organisation pledged telescope time at its major observatories and offered to coordinate a global observation network for tracking 3I Atlas as it receded beyond Jupiter orbit. The proposal included real-time data sharing protocols and standardized analysis methods to ensure consistency across international observations. The organizational framework could serve future interstellar visitor studies if implemented successfully. The coordinated international response reflected recognition that 3I Atlas transcended national interests and political boundaries. Whatever it was, whatever it meant, the implications concerned all humanity equally. Space agencies that typically guarded proprietary data and competed for scientific prestige were sharing information freely and coordinating efforts with unprecedented openness. The shift from competition to cooperation happened organically, driven by the magnitude of what everyone was facing. Some discoveries are too important for institutional rivalry. Some questions affect everyone equally. 3I Atlas had become one of those questions. The international response acknowledged that we were all in this together, watching something that might change everything we thought we understood about our place in the universe. The confirmation that 3I Atlas likely represented artificial technology forced astronomers to reconsider fundamental assumptions about our local region of the galaxy. For decades, the search for extraterrestrial intelligence focused on detecting radio signals from distant civilizations light years away. 3I Atlas suggested a different scenario: active exploration using physical probes rather than passive broadcasting. If 3I Atlas was a reconnaissance vehicle, then similar objects might be common throughout nearby space. The galaxy could contain networks of automated explorers moving between stellar systems, gathering data over millions of years. This paradigm shift transformed the search for intelligence from listening for distant signals to recognizing visitors already present in our cosmic neighborhood. Statistical analysis of the 3 detected interstellar objects supported the probe hypothesis. 2 of 3 visitors showed anomalous properties. If this ratio held for the larger unseen population, interstellar space might contain more artificial objects than natural debris. The implication was staggering. Humanity's first systematic survey of interstellar visitors immediately encountered technology rather than nature. The trajectory analysis of 3I Atlas revealed it had passed near at least 3 other stellar systems in the past 80,000 years. If it was collecting data, those systems had already been surveyed. Earth might not be this probe's first contact with planetary civilizations. We could be one target among many in a comprehensive mapping program spanning the local stellar neighborhood. Astronomers began re-examining archival data, searching for previous visitors missed by earlier surveys. Fast-moving objects dismissed as asteroids with unusual orbits received renewed scrutiny. Several candidates emerged showing trajectories consistent with interstellar origins and properties that didn't quite fit natural classifications. The historical record might contain evidence of earlier visits that weren't recognized at the time. The Vera Rubin Observatory's imminent operations took on new urgency. If automated probes regularly transit our solar system, Rubin's wide-field surveys would detect them within years. The expected discovery rate of dozens of interstellar objects annually would reveal whether 3I Atlas represented an isolated anomaly or the first recognition of common phenomena previously invisible. The galactic neighborhood suddenly seemed more crowded and more interesting. The question wasn't whether intelligent life existed elsewhere. The question was whether it had been quietly studying us for longer than we realized. 3I Atlas suggested we weren't discovering alien intelligence. We were finally noticing it had already found us. The cosmos wasn't empty space separating isolated civilizations. It was a neighborhood with traffic we were only beginning to recognize. The Fermi paradox asks why we haven't detected evidence of extraterrestrial civilizations, despite the vast number of stars and planets in the galaxy. One proposed answer is the Great Filter, a hypothetical barrier that prevents most civilizations from reaching technological maturity and spreading across space. The question that keeps scientists awake is whether this filter lies in our past or our future. 3I Atlas provided disturbing new data for this calculation. If the object was indeed artificial, it proved that at least one civilization had achieved interstellar travel capability and maintained automated exploration programs over geological timescales. This civilization had passed whatever filters might exist between primitive life and advanced spacefaring technology. They had solved propulsion, power generation, autonomous systems, and long-duration engineering. They had survived, but the existence of their probe in our solar system raised uncomfortable questions about why we detected no other signs of their presence. If they possessed interstellar travel, why no radio signals? Why no obvious megastructures altering stellar spectra? Why no evidence of widespread colonization or resource extraction. The silence accompanying their evident capability suggested possibilities, none of which provided comfort. Perhaps civilizations that reach interstellar travel capability choose stealth and observation over expansion and communication. They explore quietly, gather data, and avoid revealing themselves to younger civilizations. This scenario implied intention behind 3I Atlas's apparent reconnaissance mission. We were being studied, but not contacted, watched, but not disturbed. Alternatively, the civilization that launched 3I Atlas might no longer exist. 80,000 years provided ample time for catastrophe, whether self-inflicted through war or environmental collapse, or imposed by external forces. 3I Atlas could be an orphaned probe, continuing its mission long after its creators perished. This scenario suggested the Great Filter might lie beyond interstellar travel, that achieving such capability doesn't guarantee long-term survival. The most unsettling possibility suggested that interstellar probe networks themselves represented the filter. Perhaps civilizations routinely achieve automated exploration, but this capability somehow leads to their downfall. The technology that enables spreading across the galaxy might carry inherent risks that eventually doom its creators. 3I Atlas changed the Great Filter calculation fundamentally. The filter couldn't be as simple as developing technology or achieving space travel. At least one civilization had cleared those hurdles. But the absence of obvious galactic-scale presence suggested filters remained, either preventing widespread colonization or causing civilizations to choose invisibility. We had evidence that someone had survived to build interstellar probes. We had no evidence they still existed. That combination was perhaps more frightening than finding ourselves alone. Governments began quietly updating protocols and contingency plans in late October 2025, as the reality of 3I Atlas's probable artificial nature settled into institutional consciousness. The preparations occurred without public announcements or formal policy changes, operating through existing frameworks for managing unexpected scenarios that might require coordinated international response. Planetary defense systems designed to track and potentially deflect hazardous asteroids received expanded mandates. The networks now included provisions for monitoring objects that showed signs of controlled motion or non-natural behavior. Detection algorithms were updated to flag not just collision risks, but also anomalous trajectory characteristics, unusual spectroscopic signatures, and organized emission patterns. The goal shifted from preventing impacts to recognizing intentional visitors as early as possible. Space situational awareness programs expanded their monitoring of cislunar space and near-Earth environment. Additional sensors came online focusing on detecting objects with low radar cross-sections or unusual thermal properties. Military satellite tracking systems began dedicating resources to searching for visitors using stealth technologies or materials designed to minimize detectability. The assumption that everything in near-Earth space was human-made or natural debris no longer held. Communication protocols received careful review. Existing SETI guidelines for handling first contact scenarios assumed radio signals from distant stars, not physical visitors already in our solar system. New frameworks addressed what actions humanity should take if 3I Atlas or similar objects demonstrated active attempts at communication. Questions about who speaks for Earth and what messages would be appropriate had no consensus answers. Scientific organizations established rapid response teams that could coordinate observations and analysis if future interstellar visitors were detected. The infrastructure built around 3I Atlas, including international data sharing and multi-wavelength observation campaigns, became templates for standardized procedures. Future visitors would receive immediate coordinated attention rather than the improvised response that characterized early 3I Atlas observations. International treaties governing space activities faced scrutiny. Existing agreements assumed all space objects were either natural bodies or human artifacts. They contained no provisions for encounters with non-human technology or protocols for investigating objects of potentially artificial alien origin. Legal scholars began drafting amendments and new frameworks without publicizing the motivation behind their work. The preparations reflected practical recognition of changed circumstances. 3I Atlas demonstrated that interstellar visitors could appear with little warning and display characteristics beyond our current understanding. Whether hostile, benign, or simply indifferent to our presence, such visitors required humanity to be better prepared than we were when 3I Atlas arrived. The protocols being updated wouldn't prevent future encounters, but they might help us respond more effectively when the next visitor appeared. By early November 2025, researchers had accumulated sufficient data to perform comprehensive Bayesian analysis, comparing the probability of natural versus artificial origin for 3I Atlas. Bayesian reasoning updates probability estimates as new evidence accumulates, providing mathematical frameworks for evaluating competing hypotheses. The results quantified what many had concluded intuitively. Natural explanations had become statistically untenable. The analysis began with prior probabilities based on existing knowledge before 3I Atlas's discovery. Natural interstellar objects should vastly outnumber artificial ones, simply because nature produces far more debris than any plausible number of civilizations could manufacture. Prior probability for natural origin started near 99.9%, reflecting reasonable assumptions about galactic demographics. Each anomalous observation updated these probabilities. The low density reduced natural probability by a factor of 10. The organized magnetic field reduced it by another factor of 20. The isotopic anomalies contributed another factor of 50. The trajectory corrections added a factor of 100. The infrared emission spectrum contributed another factor of 30. The brightness harmonics, the nickel emissions, the thermal management, the perihelion behavior. Each observation shifted probability further toward artificial origin. Multiplying these factors through Bayesian updating produced a final probability estimate. Natural origin probability dropped to less than 1 in 10 million. Artificial origin probability correspondingly rose to over 99.999%. The mathematics couldn't prove artificial origin with absolute certainty, but they demonstrated that maintaining natural explanations required invoking increasingly improbable coincidences. Critics of this analysis argued that individual probability estimates contained subjective judgments about what constituted natural versus artificial characteristics. Perhaps the assumed factors were too aggressive. Perhaps natural processes we don't understand could explain multiple anomalies simultaneously. Perhaps our intuitions about what's possible in nature were incomplete. Sensitivity analysis addressed these concerns by varying the probability factors across wide ranges. Even using conservative estimates that assumed half the observed anomalies could have natural explanations, the final probability for artificial origin remained above 99%. The conclusion was robust across reasonable variations in assumptions. The evidence synthesis revealed that 3I Atlas had passed from interesting anomaly to probable artificial object through cumulative weight of diverse observations. No single measurement proved the case definitively, but the combination of low density, organized fields, engineered chemistry, controlled trajectory, selective emissions, and geometric regularity created an evidentiary picture that natural processes couldn't plausibly explain. Science rarely achieves absolute certainty. It accumulates evidence until one explanation becomes overwhelmingly more probable than alternatives. 3I Atlas had crossed that threshold. The mathematics said what many hesitated to state plainly. We were almost certainly observing technology from another civilization. Astronomy divided into before and after 3I Atlas, just as physics divided into before and after relativity. The shift wasn't immediate or dramatic. No single announcement changed everything overnight. Instead, accumulated evidence gradually forced acceptance of a conclusion that seemed impossible just months earlier. By December 2025, the scientific community had crossed a threshold it couldn't uncross. The new reality meant that humanity was not alone and never had been. Other civilizations had existed long enough to develop interstellar travel, and possessed sufficient interest in our corner of the galaxy to send reconnaissance vehicles across dozens of light years. We were being observed, had been observed, and would likely continue being observed by technologies we were only beginning to recognize. Educational institutions updated curricula to reflect changed understanding. Astronomy courses now included sections on detecting artificial objects among natural populations. Engineering programs added modules on long-duration autonomous systems and interstellar mission architecture. Astrobiology expanded beyond searching for microbial life to considering technological signatures and probe-based exploration strategies. The Vera Rubin Observatory began operations in early 2026 with modified detection algorithms specifically designed to identify objects showing characteristics similar to 3I Atlas. Within the first month, 3 candidates emerged, requiring follow-up observations. 2 proved to be unusual but natural asteroids. The third remained under investigation with properties that suggested possible artificial origin. The discovery pipeline that once hoped to find one interstellar visitor per year was now routinely flagging potential technology. Public consciousness adjusted more slowly than scientific consensus. Polls showed majority acceptance that 3I Atlas was probably artificial, but deep internalization of what that meant took time. We were like children discovering their home sat in a neighborhood they'd never noticed, suddenly aware of larger contexts and implications that had always existed but remained invisible until now. The philosophical impact ran deeper than headlines suggested. Every assumption about humanity's uniqueness or cosmic isolation had to be reconsidered. Every question about our future in space gained new context from knowing others had already solved the problems we were just beginning to address. The universe hadn't changed. but our understanding of our place within it had transformed fundamentally. 3I Atlas continued outbound past Jupiter, its trajectory carrying it back toward interstellar space. Telescopes tracked it until it faded beyond detection limits in mid-2026. But the questions it raised and the reality it revealed would remain long after the object itself disappeared from view. We lived in a universe where intelligence had spread between stars, where automated explorers mapped the galaxy, where Earth was one target among many in surveys spanning geological time. 3I Atlas crossed Jupiter's orbit in late March 2026, continuing its journey back into the darkness between stars. Telescopes tracked it as far as technical capabilities allowed, watching it shrink from a detailed target of intensive study to a faint point of light, and finally to nothing at all. The last confirmed detection came from the Hubble Space Telescope on May 12, 2026. After that, the object merged with background noise and disappeared. But the data kept coming. Months of observations still required analysis. Thousands of images needed processing. Spectroscopic measurements awaited detailed modeling. The Juno encounter data, collected during those 8 hours in March, contained terabytes of information that would take years to fully understand. 3I Atlas had left our instruments, but it hadn't left our science. More importantly, it hadn't left our awareness. Every night, astronomers pointed telescopes skyward with changed perspectives. Every survey scan searched not just for rocks and ice, but for visitors that might be watching back. The SETI programs expanded beyond radio searches to include systematic monitoring for objects showing the characteristics that 3I Atlas had displayed. We were listening and looking in new ways. The waiting had 2 aspects. First, we waited for 3I Atlas itself. The object would take roughly 30,000 years to reach the nearest neighbouring star system, assuming it maintained current velocity and heading. Whether it would transmit data back to its origin, continue onward to other targets, or simply continue its autonomous mission in silence, remained unknown. We might never know what it did after leaving our view. Second, we waited for the next visitor. Statistical models suggested interstellar objects passed through the inner solar system several times per year. If even a small fraction carried artificial origins, we should detect another anomalous visitor within months or years. The Vera Rubin Observatory would provide our best chance, scanning the sky with unprecedented completeness and sensitivity. The waiting was active rather than passive. Humanity prepared, improved detection systems, developed protocols, and trained a generation of scientists to recognize what might arrive next. We watched the sky knowing it watched back. 3I Atlas had delivered a message without words. You are not alone, you never were alone, and you will see us again. Whether that knowledge brought comfort or concern depended on perspective. But it was knowledge we could no longer ignore. The waiting had begun, and it would define how humanity understood its place in the cosmos for generations to come.